Hello, my name is Nathan Dunnigan, and this is my lab report for our first lab discussing constant velocity and the relation to Newton's second law. This lab focuses on Newton's second law, constant velocity, net force, and systems versus surroundings. Newton's second law, which is also known as the momentum principle, can be used to predict the behavior of objects. It is a summary of the way interactions affect motion in the real world. The change of momentum of a system is equal to the net force acting on the system times the duration of the interaction. This time interval, or delta t, must be small enough that the net force is nearly constant during this time interval. The net force acting on a system at an instant is the vector sum of all the forces exerted on the system by all the objects in the surroundings at that instant, which I'll talk about in a few slides. When net force is zero, an object is assumed to either be at rest or in constant velocity. And then finally, constant velocity occurs when the speed doesn't change. The purpose of this experiment was to compare an experimental model to a computational model investigating the motion of an object that is moving at a constant speed without changing directions. In this experiment, the system is a basketball and the surroundings are the forces acting on the ball. If there is no net force acting on the system, then velocity will remain constant. And the graph I added previews what my modeled graph should look like, as this graph illustrates what constant velocity looks like. And here are the equations that will be used in this experiment. We have Newton's second law, which is force equals mass times acceleration, and we know that net force will be zero because of constant velocity, so that means acceleration is zero. And then we have final position equals initial position plus the average velocity times delta t, and then we have final velocity is equal to initial velocity plus net forces divided by mass times delta t. Here's my experimental model, and I'm going to explain this model as I show you guys the video. So this model demonstrates net force of an object, and as you can see, the red dots correspond to the data in the table to the right. There's a positive slope as seen in the upper graph, and the graph is showing the relationship between position and time, which is that first graph up here. And now my computational method, I had to set some initial conditions demonstrating the starting condition. And this highlights how the graph was plotted. I wrote this code using Python and Glow script. I set the mass equal to 0.625 as this is representative of the mass of a basketball, which is what I just used in my experimental method. The initial position is equal to 0, 0, 0 as my object starts moving from the origin. I set the initial velocity equal to 3.600, which remained constant throughout the entire process as my object illustrates constant velocity, and I used the data from the tracker application to find this initial velocity. I also set delta t equal to 0.01 as it is necessary that delta t is small enough so that the net force on the system does not change significantly during the time interval, which can be found by dividing the total length of the video by the number of frames used in my experimental method. And here is my computational method and the code that illustrates how Newton's second law and the final position and final velocity equations are used, which I talked about earlier. And the net force was set to 0, 0, 0 because the object has a constant velocity, which means there is no external force. And you can see the two equations that I just talked about right up here. Those are the two equations. And this is the graph that shows the difference between my experimental and computational model graph. And what does this graph mean? The graph illustrates an almost identical slope for both models with a positive upward trend as time increases, which suggests that the computational model is a good estimate of the experimental model. The experimental model is a little less consistent than the computational model, which could be because the conditions when rolling the basketball were not 100% perfect, which may have resulted in a little friction, which might be a source of error. However, both convey that there's a positive correlation between time and position, and both show that there's constant velocity. And here are some follow-up questions. So what if positive x and negative x were interchanged? The slopes of the graph would be downwards rather than upwards. However, the conclusions drawn would still be the same, as constant velocity would still be shown. As times increased, the two models diverged slightly due to causes of friction. This could affect the constant velocity as the net forces acting on the system would not be equal to zero. To fix this in the future, we might use an object that has very low coefficient of friction or accounting for the friction forces in the computational model. Also answering the question, is it possible to know how many forces are acting on an object? It's really not, and the net force should be equal to 0 because it is a constant velocity. And this whole experiment still illustrates that there was constant velocity, which was seen in the graphs, which were created using the data from my two models. Thank you for listening. Have a good one.